Hello and welcome to our presentation on hydrogel-based DIY underwater morphing artifacts. I am Kexin Lu from the Morphing Matter Lab at Carnegie Mellon University, and along with my teammate Harshika Jain and Professor Ning Yao, who is also the lab director, we have done this work to democratize the creation of such hydrogel-based morphing artifacts. We are excited to be presenting our work to the HCI and design community here. We want to kick it off by presenting some of the advanced designs of these hydrogel-based artifacts.
You might be wondering how these transformations happened. So starting out with talking about the material, hydrogels. Hydrogels are capable of absorbing about 10 to 1,000 times their weight or volume of water. To create the artifacts we just showed, we adhere hydrogel beads on a substrate and immerse them in water. And as the beads expand by absorbing the water, it causes the substrate to bend. By varying the distance between these adjacent hydrogel beads, we can control the morphing and bending angle of these artifacts, and this leads to the beautiful transformations that you just saw.
Coming to the motivation of this project, we found that most shape-changing interfaces require advanced material synthesis, specialized lab settings for fabrication, and technical knowledge to simulate their morphing behaviors. Additionally, the cost of procuring the material is very high. These factors become a barrier for makers who want to create and replicate such structures. We want to therefore democratize the creation of such artifacts and extend their design space with low-cost, easily available off-the-shelf materials in the shape-changing community.
In our presentation today, we will be talking about our low-cost and easy fabrication process, which enables a large audience to create morphing artifacts, along with some of our advanced explorations. The process of developing a computational tool along with its user-friendly workflow, and the bending angle quantification experiments for creating the simulator. Starting out with how these artifacts can be made, we will talk about our step-by-step design process. Following this process, anyone without prior knowledge of numerical and computational techniques to create morphing structures would easily be able to get started.
Our computational design tool can be used to specify the outline of the substrate. Otherwise, a user can select a basic branch or kirigami outline from the library to start off with. This is a generative shape library for branching, and this is for kirigami, and both of them can automatically suggest layout passes for beads. The user can then generate infill patterns that will fill the outline of the substrate automatically and adjust geometric features of the infill pattern lines, such as the total number of hierarchies and roundness of each corner. Then the user needs to specify the layout of the beads and select pattern lines to locate the actuation. The bead's placement is generated along those lines, and the bead's distance can be adjusted to control the bending curvature. The side of the substrate on which the beads will reside can also be defined. Then the structure is ready, and user can simulate it in the tool and iterate to achieve the desired shape and transformation. The outline of the substrate can be exported, laser cut, and beads locations can be marked with a CNC plotter. Beads can be attached to the substrate using superglue. Sequential transformation of the branch or kirigami structure then occurs. Using our tool and fabrication method, we created 4 typologically complex demonstrational artifacts, in which the morphing stimulus comes from water itself. Branch artifacts, inspired by underwater plants, biomimetic and organic. They are constructed by multiple layers of substrate, and the bead placement is such that it leads the layers to bend inwards. Kirigami artifacts. The benefit is that structures can morph from a single flat shape to a fully open blooming state. further pushing the limits of flat packing and space-saving deployment.
Coming to the DIY aspect, we created a DIY toolkit to enable anyone to design and fabricate morphing structures easily. What we showed just now is a demonstration of the kind of advanced explorations that can be made with our technique. The DIY toolkit has substrate outlines printed on gateway sheets or vellum paper, hydrogel beads, superglue, a pair of tweezers, and a bead placement tool. To onboard users to create these morphing artifacts, we provide already designed samples of the substrates that have a predicted morphing behavior on which markings are pre-made for placing the beads. Users can see a transformation by simply cutting out the patterns of the substrate, applying beads, and deploying them in a water tank. Post this, users who develop further interest can start using the computational tool as well and execute the design to fabrication process end to end. We have received a great interest from K 12 classroom teachers to make their students use our toolkit and are planning out the workshops also. In the short term, we will run these workshops and use the learnings to improve the toolkit. And in the longer term, we plan to build on this research and create more robust artifacts for potential coral conservation efforts. Now, coming to the question about how did we develop the tool? We conducted quantitative experiments by attaching hydrogel beads 3 mm, 4 mm, and 5 mm apart on flexible substrates like woven cotton and paper. We observed that by changing the gap distances between the beads, we can control the maximum bending angle. This helped us to remap the domain of parameters such as the expansion rate of the beads.
Based on the experiments, we were able to explore more possibilities of this bending analog by playing with different bead distance. These are the examples of uniform bead spacing and variable bead spacing. We place beads on both sides of the substrate to achieve an even more unique bending aesthetic. To accommodate diverse substrate patterns in our simulation model while keeping the underlying model simple and fast, we divide a given structure into 3 basic geometric elements: beads, line, and substrate. These 3 geometric elements are employed as the physical model to define the simulation of bead expansion and collision, which determines the quantitative bending behavior. Based on these experiments, we create a rich vocabulary of morphing primitives to serve as a geometric reference for people who would like to create such kind of structures.
There are limitations in our fabrication process, scalability, and deployability, which have opened up many new avenues and directions for developing the tool further. For instance, the current simulation model considers the substrate as a thin sheet without accounting for its thickness. In reality, if beads were adhered to a harder or thicker substrate, such as a metal sheet, the bending behavior would be much different than what it is for a flexible substrate. Additionally, the bead layout is also limited to individual straight lines. In the future, we hope to include more complex actuator patterns such as curved lines or diagonal patterns. Additionally, currently the bead application process is manual and it serves as a solid proof of concept, but in the future, this process can also be automated.
To summarize, this paper offers a novel DIY approach to produce shape-changing actuators with low-cost hydrogel beads and broaden the potential for their use through a simulation tool and a quantitative method. Utilizing simple materials and easy-to-use tools, one can easily design and create a variety of fun designs to include in the fish tank. With this, We conclude our presentation and are happy to answer any question. Thank you.